Is there a particular question that's bothering you on the list? Well, I don't have time to go over everything. I guess I can do a couple questions. Yeah, you have a question on this?
Should I just read out the question? It's number 3 on the 4.
Number what?
Number 3 on the B list.
What version do you have?
B.
B. Number 3?
Yes.
Okay, so this is quiz 4. This is run version B. It's well, it's 3 from version B, and it's actually 1 from version A. Where I ask you to write down an equation that defines when a function is continuous at a point x equals n. That's it. Right? I gave you the definition with A here, but it doesn't make a difference, right? The limit as you approach the point is actually equal to the value of the function at the point. That defines continuity in a single equation, right? And I drew all the pictures there when I was talking about. Okay. Other questions?
2E on 4B.
2E. This is version B. This was the limit as x approaches 0 of 1 over x minus 1 over absolute value x. I believe on version A, yeah, I let you approach 0 from the right side. Okay, so what do you do here? You have an absolute value around 0 when what's inside the absolute value is 0, so you have to consider like both directions, right? So you have to think about as you approach 0 from the left side what happens, and as you approach 0 from the right side what happens. Right? So from the left side your function actually behaves like 1 over x minus, well, absolute value when you're less than 0 is actually gives you negative, so this will give you plus. So this is just the limit as x approaches 0 from the left of 2 over x. And as you approach 0 from the left, this goes to negative. When you're positive, your absolute value actually returns positive x, so this just becomes that. And so that's just the limit of 0. So this is 0, which means that this guy does not exist. And for those of you on version A, this would be 0.
the O minus, right? If you put 0 in the bottom, then doesn't it become 200?
You can plug 0 in the bottom. Division by 0 doesn't make any sense. You're approaching 0 from the left. And this graph looks like that. As I get closer to 0 from the left side, I keep going down. I never actually plug in 0, I just get closer. That's what limits care about, getting close to things, not actually being there. Other questions?
Can you go over on 2A, on 4A? Please, 4A.
2A?
Yeah.
It's actually asking the limit as x approaches 0 cosine 2x over 4 plus 2x to the 4th. What do you guys think that's equal to? Yeah? It's 1 over 4. How did you get that? Just plugged in 0, right? Right, it's defined everywhere, actually. Right? When you plug in 0, the denominator is not 0, so there's no problem with just plugging in. The cosine is defined everywhere, this is defined everywhere, and the denominator is not 0, so literally just plug in 0. Right? This is just cosine cubed of 0 over 4 plus 2 times 0. Yeah, it was just a plugin. You didn't have to actually do anything other than that. Which sort of, I guess, brings me to a general approach to limits.
Professor?
Yes?
Yeah, you marked it wrong for 2E. I have it right.
2E?
Yeah, it doesn't exist. I put DNA, and you marked it wrong. I have 4B.
Oh, I don't know. Okay, maybe I was going to learn. See me after class. General approach. Right, so the solutions are on the website. So if you see like you had the right answer and I gave you the wrong, I deducted a point, just let me know. General approach to limits. Hopefully, by doing a lot of the limit problems, you would have come across all these situations that you know to look out for. I'm just defining x approaches a of x, for example. So one, if f of x is defined at a, let's plug it in, right? i.e., the limit as x approaches a of f of x will actually be f of a, right? So this means if you can plug in the thing and it doesn't divide by 0, you don't get a negative under a radical or something like that, it's okay to just plug in the answer, right? It's the first thing you're going to look for. So if I give you a random limit, the first thing you're going to check, can I plug in the number, right? And if you can, and there's no problem, you just plug it in, right? Of course, there are cases where you can't just plug in the number. So if plugging in is a problem, try to simplify to cancel the problem. Right? So if you're trying to plug in something and you realize, oh, the denominator is going to 0, what you're going to do is try to simplify and see if you can actually cancel that part of the denominator that's giving trouble. Right? So you try to plug in, that's the first thing you try to do. That doesn't work, try to simplify and cancel the problem. Right? Sometimes that will work. But this is sort of the order of things you try to do when you approach a random limit problem. Trick is involved. Try to manipulate so very typically in this course, if you have a trig limit, most of the time we're gonna try to figure out if you know how to use a special trig limit. So this is, are those guys like x approaches 0, sine x, so x equals 1, etc. Those guys that I gave you before. Right? And again, this doesn't have to be exactly x. It can be whatever expression as long as it's in the angle and it's in the denominator and it goes to 0, and what this limit is doing, that will give you 1. So it would also apply to something like x approaches 1 sine x minus 1 over x minus 1. Right? So that would also be 1. Right? So it doesn't have to just be x, it can be anything, as long as it approaches 0 as its limit. And of course, you may have to use, trig identities prior. So yes, you are expected to remember your half-angle formulas, your Pythagorean identities, all that. They would expect you to know this, right? And be able to manipulate them.
What was time there was another, you know the triple trig thing that you said?
Yeah.
Trig thing? 1 over cosine theta equals 1.
The limit as x approaches 0? Well, theta approaches 0, you mean?
Yeah. Of 1 over cosine. It equals
Yes.
1. Alright, so you didn't tell?
What?
You didn't tell us that.
This falls under problem 1. I can actually plug in theta equals 0. Cosine of 0 is 1. I would just plug it in. This is just cosine of 0, which is 1. It's covered by case 1.
Okay.
Just plug it in. There's no
It's
problem.
not like a rule.
Yeah. You don't have to know it because it's one of those things where you just plug in. Yeah. So that's covered by 1. 4. If f of x includes an absolute value, you must check the one-sided limits if A makes All right, so example. Alright, so here's a part in absolute value. What happens when x approaches 1? The inside of this goes to 0. Once that happens, you have to actually split it in 2, right? You have to think about what if x goes to 1 from the left, and what if x goes to 1 from the right? Right? So once the thing inside your absolute value is going to 0 as you're taking the limit, you have to consider both sides, because the sign will actually change, and that might affect the answer. Right? If I had limit as x approaches 2 of the same guy, here I wouldn't need to worry about the one-sided limits, right? Because this guy is not going to 0, right? There's no reason to test what happens on either side. I just know that when x is 2, this guy is positive, so the absolute value will replace this with plus x minus 1, right? So here I'd only need one side, right? I would just realize that this is just x approaches 2 of x squared minus 1 over x minus 1 and find that limit. Or if I know x is approaching minus 2, then I know that I just equate this to x squared minus 1 over minus x, right? But I won't have to check both sides. You have to check both sides when what's inside is going to 0, right? So this is something you always have to worry about. Once you see absolute value, you have to check, is the part in absolute value going to 0? If it is, you have to do both-sided limits. Because on both sides of where this guy hits 0, we will actually flip the sign. So that's going to be, well, you know, those are just some of the things you should be picking up from doing your limit problems up to this point. There are other, like, you know, little nuances and clues that you'll get. But yeah, you see a random limit problem, the first thing you're going to do is try to plug it. If that doesn't work, try to simplify to cancel whatever the problem is. If you see trig, try to think of the special trig limits. If you see absolute values, worry about if you have to break it up. Right? These are just some general things you consider when you approach the random limit problem. We're going to move on and finish up continuity. We had the definition last time. So I gave you the definition. I drew a bunch of pictures. So let's just move on to some examples. Work on those for now. So let's start on A. Where is that continuous? Meaning, tell me the interval on the real line of all x values that will make this function continuous.
All real number x is 0.
Okay, how do you know it's not continuous at 0?
X doesn't exist at 0.
Now when it comes to continuity, what do you have to show?
That we can go over the line without putting our pen up.
Algebraically. Right? Because I mean, for each of these, you don't want to have to like graph them to see if you can draw them, right? The limit and the function have to equal each other, right? So remember, recall, f of x is continuous at a if the limit as x approaches a of f of x equals f of a, right? So three things must happen. One, the limit must exist. Two, oh, and by the way, when limit exists, sometimes you have to check both right and left hand, right? So right and left must exist and agree. So that's the first thing, right? This is saying you have to be able to find the limit, right? Two, the function must be defined at the point. And three, one must equal two, right? You must have the limit equal the definition, right? So those are three things you want to check. So if I wanted to check those three things here, how would I go about it? So, first note, if x is not 0, everybody's continuous, right? Right? So as long as we're not at 0, 2 is continuous and this is continuous, right? Because you're not dividing by 0, right? So as long as you're away from 0, everything is hunky-dory. So now you have to worry about at 0. Now at 0, what do you have to show? You have to figure out, does the limit as x approach 0 of f of x equal f of 0? Right? That's what you have to check, right? So how do we check this? What's the limit as x approaches 0 of f of x? So here I have a piecewise function. It's defined when I'm not at 0 and defined when I'm at 0, right? Remember, limits don't care about being at the point, right? So when I'm looking at the limit, this is the function I'm looking at, right? The one where I ever accept 0. So I'm really just looking at this guy. This is equal to 1, right? So limit exists. Check. All right, so the second thing we have to do is the function defined. F of 0 equals what? 2. So f of a defined. Check. What's the third thing now you have to look for? Does the limit equals the value of the function? No. Right? So, wrong, right? So, not continuous at 0. Therefore, where is it continuous? Everywhere else we're fine, but 0 is a problem. So, ever except 0. Any questions on that? Here's a question. Could you redefine f of x so that it is continuous? Is there a way you can fix your function such that you don't get too different? Don't want to do a whole different thing by moving one point or multiplying. Is it possible to do this? How will you fix it? Right, you can just redefine f of x to be sine x over x, as long as x is not 0, but then make this 1 instead of 2 when x is 0. And that function will actually be continuous everywhere. You actually fix the problem. Because the problem here was your function is doing whatever it's doing. And it's approaching 1. But at this point, your function was defined here. So what you can do is just, since that point is the problem, just take him and put him down here. That's one option, right? On the board, you could have done something like, just multiply this guy by a 2. But this one is really the main one. Whenever you can fix a point of discontinuity by just moving one point, you call it a removable discontinuity. In this case, we call the discontinuity removable. Since you can sort of fix it by minimally redefining the function, we call it a removable discontinuity. Yes, we're discontinuous at 0, but it's not such a big deal. You can just move a point and it's all fixed. Right? Yeah. Yeah, so there are times when limits are used in applications and you're like, oh, this thing isn't working. Can we salvage things, you know? You can say, yeah, if we just fix this little part right here, everything works, right? There are times when it just doesn't work. Things are just really bad, right? But in this case, there are simple things you can do to fix the problem. And whenever you can do that, you say, oh, it's removable, right? It's discontinuous there, but it's not like the end of the world, you know? You can fix things. There are things that can't be fixed as far as limits are concerned. Our second example. So remember, this was f of x equals x squared plus 5x plus 6 over x plus 2. Where's this continuous? What happens at minus 2?
Discontinuous.
It's discontinuous at minus 2, but everywhere else it works. That's what you think? Okay, prove your claim. How would you go about proving that it's discontinuous at minus 2? Right, so you know as long as x is not minus 2, we're fine, right? Right, because we're not minus 2, then the denominator is not 0, and we can get real numbers from this. That's fine. Right? Now at x equals minus 2, what happens? You have to check, does the limit as x approaches minus 2 of f of x equal f of minus 2, right? That's the question, right? If that's true, then it's also continuous at minus 2. If it's not true, then it's discontinuous at minus 2. All right, what's that equal to? How do you know it's equal to 1?
The first one.
Right, it's just going to be this guy, 5x plus 6 over x plus 2. Right? So the first thing you try to do, plug in the point. Can't plug in the point, denominator is 0. So what do you try to do? Try to simplify. You'll see it here, you can try to factor this. X plus 2 times x plus 3 over x plus 2. We've canceled the problem, and now we can actually plug in minus 2. So this actually gives me the value of 1. The limit is equal to 1. So f at minus 2 is equal to, it's equal to 1 by definition. So since you notice that the limit is actually equal to the value of the function, f of x is continuous at minus 2. And therefore, f of x is continuous everywhere. The only possible thing that could go wrong is at the point minus 2, because you might have, you see here you divide by 0. But then when you work through it, you realize, oh no, we fixed it with this thing, right? So what happens is this graph actually looks like that, but there's a hole in it at minus 2, which is going to be here, roughly. That hole happens to be at the level 1. And then we just went over here. Oh, at this point, make that the value. So we actually shade in this point here. So there was a little gap and we bridged the gap. So this is continuous, there's nothing wrong with it. This function you could actually draw without lifting your pencil off the page. Right? It looks complicated, but it turns out you can do it. It's actually a straight line. look at another example. Oh, I did I have a third one? I did. That was it, right?
Yeah, he did the same.
Okay. Where is that continuous? What do you mean at 1? Where it's continuous? Okay, so here you realize that f of 1 is undefined. So discontinuous. X equals 1. Right, that's it, right? Once it's not defined there, you don't have to worry about anything else, right?
What do you mean by
Like I can't actually plug in 1 and get an answer, right? Because I'd be getting 0 in the denominator. Undefined just means it doesn't have a value. There's no value you can assign to this thing. Can we fix it? Could we somehow redefine this function to eliminate the problem? How would you redefine the function? Okay, well, yeah, you can realize that this guy is actually x3, x1. What? Plus 3 minus 1. Right, so this would cancel. And you have x plus 3. So does that give you a hint as how to redefine this? If 1 equals 4. Right? Notice here, you know 1 was the problem, so approaching 1 is the problem. So what you want to do is figure out, when you simplify it, what value would it be if you plugged in 1 at that point? Right? And it turns out that if you define it to be x squared plus 2x minus 3 over x plus 1, if you're not at the problem point, and actually define to be 4, when you're at the problem point, then it's actually fixed, right? So it was removable. Right? You can change it by simply fixing a point, because your limit was actually 4. So you really want the limit to equal to whatever the definition is. So whenever that works, you get continuous, and you can fix it. There are cases when you can't really fix it without getting a whole new kind of function. Right? So I mean, a simple example is this is discontinuous at 0. Obviously, because you can't plug in 0 and you can't simplify to get rid of the problem. Right?
Wait, for the last one, if you simplify...
If I simplify this, I get x plus 3. And if I plug in 1, I would get 4.
So why do you say it's undefined?
It wasn't defined at 1, right? Because I couldn't actually plug in 1, right? If I plug in f of 1, I would divide by 0. Undefined, divided by 0.
Can't you simplify first and then plug in?
If you're finding a limit, yes, but there was no limit. Yeah? It depends on how the question is phrased, right? So if the question is just, is this continuous? You just say yes or no, and you justify, right? But it's a totally different question to say, is it removable, right? then you can say, oh yeah, I can fix it just by fixing this point, right? And that's fine, right? It's two separate questions. There are times when you can't fix it. For example, this one can't be fixed without completely changing the function, right? This is continuous at 0, and if you remember what this looks like, notice that to actually fix it, it's more than a gap of 1 point, right? The entire y-axis is like off limits. You literally have to fix an infinite number of points to try to get this thing to work, right? This is called an infinite discontinuity. Right, so you can't fix it by just filling in a point, right? The gap is just too big. In fact, the gap is infinite, right? There are other things that we like jump discontinuities that the book mentions. We're not going to deal with those too much. So this just means like, your function is doing something and then it jumps somewhere else, right? Again, you can't fix that by just changing a single point. You literally have to change a whole side of the function and move it up here, right? That's too much work, right? So things can be discontinuous, but there are three main categories that we sort of put it in. If it's in a category where you can just fix it by fixing a point, you call it a removable discontinuity. If it's like the gap is infinitely large, you call it infinite discontinuity. And if it's just like a jump, there's a finite space that you have to fix, but you have to move like a whole part of the function. That's called a jump discontinuity.
Professor,
Yes.
is that continuous?
This is continuous. This was not. This is continuous because I redefined it at the bad point to match the limit. Other questions?
Can you do another thing?
Of what?
Stop it. That.
How about that? I'll give you a very similar kind of problem where it's a matter of trying to make something continuous. It's very similar to what was on the quiz, and it's more like the kind of problem that I probably asked on a test. So, might sort of get you more used to the idea. Determine the values So remember, algebraically speaking, to make something continuous, you just need to make sure the limit and the value of the function match up. That's really all you're doing. And then depending on how big a gap the mismatch is, you can either be removable or infinite discontinuous or a jump discontinuous. But to sort of get you more practice with what it means to make the limit and the value of the function connect, they sometimes give you these kinds of problems, right? Sort of figure out what points you have to fill in to make this guy work. Okay, so we did a similar problem on the quiz. What did you think? Here, in this example,
Two.
Yeah?
It's only 2 times x over x equal to 2, so we have to make 3a.
It's not equal to 2, no. As you approach 0, the limit is 2. It's a very different thing.
So, but we need to make 3a equal to, right?
Yeah, essentially, right? So notice here that if we're not at 0, everything is fine, right? So now we have to worry about at x equals 0. Now we need, right, because the question is here, we need to determine how to make it continuous. We need that the limit as x approaches 0 of f of x to be equal to f of 0. Right? That's what we need to happen. Right? In other words, what this means is you need the one-sided limits to match up, and you want their values to be f of 0. You want the one-sided limits to give you the same value, and it must be equal to the definition of the function at that point. Right? That's what you need. Okay? So how do you make sure that happens? On this side, what would you need?
2 sin x over x equals 3a.
This is the limit as x approaches 0 from the left of 2 sine x over x, right? Approach 0 from the left means you're looking at when x is less than 0. And that must be equal to the definition of the function at 0, which according to this is 3a. So I need that to be equal to 3a. Which means this is actually equal to what? Well, this is actually equal to 2. And then this would mean that you need your a to be equal to 2/3. So once your a is equal to 2/3, you're going to connect things from the left side. And that's good. Right? What would you need to make the right side work? Well, when you're to the right of 0, you're looking at this function. So you're doing 4b cosine x to be equal to the definition of the function at the point, which is 3a, which happens to be 2. Right? You know that it's 2 at this point. Okay? 3a is equal to 2. Right? You can plug in a equals 2/3.
What if it doesn't work? I mean,
Well, we're going to force it to work.
But,
No, we're making it work. That's what we're doing.
okay.
We're actually going to find what b has to work to get
What
to.
if we would have done that one first? Would you have gotten the same thing?
Right, well, I wouldn't have done this one first because I would have one equation and 2 unknowns. I have both a and b would be unknown. I wouldn't get any. Right? However, coming from this side, this is the only unknown. Right. So yeah, so first I did the left side to find the a, and then I can use that in order to find the b. And so this guy is actually equal to what? Just 4b, right? Because as x approaches 0 cosine, you get 1. And that, you know, is equal to 2. So this means b must be a half. So if your a is 2/3 and your b is a half, this function will actually be continuous, right? There's going to be like a point missing, but we filled it in by choosing this particular set of a and b. Right? And yeah, that was a good question, by the way. Why why did we do this one first? Well, because I would have had two unknowns at that point. Yes.
Why did you split up 4b and cosine x?
Why did I
You
split
plugged
it?
in 0 and then.
Yeah.
Okay.
Right. This is one of the cases where you can just plug in the thing because 0, it's everyone's defined. Cosine 0 is 1. Right. So I get 4b. We have a bunch of theorems to write down. There's a notion of one-sided continuity as well. Just so that you know. If you're talking about the limit as you're approaching from a certain side, like the right side, f of x equals f of a, we say f of x is continuous from the right. And obviously the other way, as you're approaching the limit on the left side, f of x, you get f of a. We say f of x is continuous from the left. Do you have an example of that? Sure. So can I ask 3 questions? Is this continuous? If so, is it from the left or the right or neither? What do you think? Just find the one-sided limits, right? So let's look at approaching 0 from the right. Maybe at if you look at coming from the right side of 0, of f of x, this is just you're taking the limit as x approaches 0 from the right side of absolute value of x over x. And what's that limit? 1, because you're positive, absolute value of x just returns x, so the answer is 1. Which happens to be equal to f of 0. So this means continuous.
Is that what you're doing in the beginning?
Huh?
Is that what, like, the first problem you did?
Similar, but I'm only concerned about one-sided things.
So how do you know if it's one-sided or not? And
Oh, well,
which
I
side?
answered it determinant. I put it in the question.
So how do you know which side then?
I'm checking both sides.
To see which one works?
Yeah.
Okay.
Continuous from the right. Now let's check is it continuous from the left. Well, if I put in as x approaches 0 from the left of f of x, and what is that? Right, your x is negative, so absolute value x is replaced with negative x, and the answer is -1, which is actually not equal to f of 0. So not continuous from the left. So here's an example of a function. It's continuous from one side. From one side you connect, from the other side you don't. In fact, this sort of function here looks like that. There's that one discontinuous. So there's a gap here, it's not continuous. I have to lift my pencil off the page before I get to that point. But here I can go right through, coming from that side. And obviously you'll see that it's not continuous. So you have to have continuity from both sides to be continuous. These guys have to connect. Being continuous is all about connecting. That's what it's about. In chapter 2, you'll see why all this is important. Being able to connect things and get close to things. And there are a bunch of other theorems you need to know about continuity. And a lot of these things that we're going over now, actually, I feel like they'll help you more in talk 2 than they will help you here. But it's actually good. It's a theorem if f and g are continuous functions. F times g minus g c times f over g if g is not equal to 0 are also continuous. Oh, also f of g. So you can build up new continuous functions from older ones, right? You multiply two continuous functions, they maintain their continuity. Subtract them. If you multiply by a constant, if you divide them, as long as the bottom is not 0, this new function will be continuous. If you plug one into the other, they will still be continuous. You can't destroy continuity by doing any of these operations. That's what it's talking about. And that's going to be important later. Another theorem you need to know.
Sorry, would C times G also be continuous?
Yes. Constant times a continuous function is also continuous. Another theorem. The following are continuous on the domain. polynomials, rational functions, trig functions. Is that all the ones you care about? Well, root functions as well. Right, as long as you're within their domain, they're continuous. You can keep drawing them without lifting your pencil off the page. Another theorem. If f of x is continuous, at b and limit as x approaches a of g of x equals b, and limit as x approaches a of x. This is just showing you one of the properties at a point that you can actually apply in general. It's one of those things that you can actually move limits inside continuous functions. So for example, this works out if you wanted to figure out what is the limit of 2 of sine x squared. It turns out because sine is continuous, you can actually think of this as sine of the limit as x approaches 2 of x squared, which is just sine of 4. Right? Like limits can move themselves inside and outside of a continuous function. That works only for continuous functions. There are other functions for which it does not work. Right? You can sort of move the limits inside them. Again, that's something that will help you a lot in Calc 2. We'll see how much it helps in here. Okay, we'll stop there.